And we move on to the second talk of the day, that is by Sougato Bose from UCL London. And he's going to talk about non-classicality with mesoscopic levitated.
Saying happy birthday to Tony. Yeah. And let me also thank the organizer for giving me the chance, the opportunity to speak in front of Tony and to, in person, to tell him the best wishes. Okay. And the topics I'm going to speak about, so Tony has actually been an inspiration. Okay, so that is how I know him. This is only my second meeting with him, so I have not met him too many times in person, but there has been an indirect influence, and it has been a great inspiration, the kinds of questions he has asked. Okay, so these type of things were transmitted to me through my interactions with Dipankar Home, who has known Tony for a long time. And essentially, literally from the earliest times when I've been working, which was with Dipankar Home, I got initiated into this program, which Tony has launched in the 1980s, or probably thinking even before that, is this aim to find experimentally oriented studies of the foundation of quantum mechanics. Okay, so you try to design experiments which will really probe the limits or the boundaries of quantum phenomena. Okay, when they hold and when they, what is the maximum mass or what is the maximum macroscopicity to which you can stretch quantum phenomena. And yesterday I put these two quotations from, I think Tony said these as a response to some question from the audience. Two of these things he said. And the two things I'll speak about are related to both these comments, in fact. So one of the things he said was does quantum mechanics still work in everyday life? What I'll hope to work towards is not yet everyday life, but we are somewhere intermediate between the microscopic world, in which we know quantum mechanics works very well, and everyday life, so which is nanoscale and microscale objects. Okay, so for them, whether quantum mechanics is working, that will be one of the lines I'll speak about. And then also, Tony said this as a response to someone, that despite the fact that now billions of electrons have been, according to his proposals, have been shown to be in superposition of moving one way or other, but still he has a problem with the Schrodinger's cat, and so we will try to stretch the Schrodinger's cat more, okay, to more accurate way. And in things I will show, will not. It's not sure that it will answer whether there is an answer to this problem at all. It is just could make this problem more acute, or it could give a strange answer to this problem. Okay, but let us. I'll go to some more details. Okay, so just I want to, by the time of Tony's 90th, hopefully, I'll have a more direct connection with Tony. So Dipankar Home and I have long been working on quantum indistinguishability's interplay with quantum entanglement, and particularly in respect to this latter paper, Dipankar had a lot of comments and insights from Tony. And then we are discussing something, so hopefully in that context, by the time, in next 10 years, there will be something together. Okay, so let me start with the first, with this quantum mechanics in everyday world, okay. So in the systems we see in everyday world, manifestly satisfy two things, okay. So one is that a given system we always find in one of the macroscopically distinct states, okay. So like a ball rolling in a well, at it's in distinct position with distinct momentum at all times. So these are things, the states which can distinguish, we find them always to be in one of those, okay. And when we observe the ball, that doesn't change its motion, right. So these are two properties which are manifestly true in the macroscopic world, and together you can call them macrorealism, okay. This is more specifically called non-invasive measurability, the second aspect. And the first aspect is what we call realism in the macroscopic world. Together, one can call it macrorealism. And Tony and Anupam Garg, in a classic paper in 1985, proposed a methodology to check it for any engineered quantum system. And this is the methodology we are going to apply to something which is probably one of the largest systems people are trying to examine quantum properties of, which is a nanocrystal or a microcrystal trapped in an optical tweezer. Okay, these people have done already. Okay, and many of my colleagues do that. Okay, including my colleague at UCL, and what they have observed is a long time dynamics of a ball, rolling that for literally forever, for a very long time. Okay, so it's a very isolated system. But the problem is that it is still a classical ball, what they have seen. Okay, they have isolated it and they are observing these oscillations. Okay, so the question is that is it quantum? So far everything they have observed about it, satisfy quite well both those macrorealism things. They are observing it that is not damping the motion, that's the motion is going on, and they are observing it, like a ball with position and momentum at each time, and that's remaining unaffected. Okay, so that's really manifestly doing everything about macrorealism. Okay. So what can one do? Okay, so this is what we, this is my collaborative work with Dipankar Home. So what we thought is we do these kinds of modular measurements, okay, of the position. So this is a kind of coarse-grained measurement. We measure whether the ball is on the left of a well or the right of a well. Okay. Practically, you can actually shine light on half of a well. Okay. These particles are observed very well by scattering light from them. It's an interferometric detection. So scattered and unscattered light is very precisely you can detect. Okay. And in a modular manner, we measure whether it's on the left of a well or a right of a well. If it's on the left of a well, we give a value -1. If it's on the right of the well, we give a value +1. Okay. This harmonic oscillator, we start it in a coherent state. So this is it's a very, this is the most classical of all quantum states. Okay. If you have to have a replacement, classical replacement for a quantum state, this is the coherent state. Okay. And then we do something else also in our methodology. What we do is we retain only those outcomes where there was no fluorescence observed. Okay? That means if the particle was not found here, it must have been there. Okay? We start the experiment when the particle rolls down and is exactly at the center, moving with momenta towards the right. That's the time of the measurement, okay, the first measurement. And we keep the outcomes where there was no fluorescence observed. Which means that there's no chance of the particle, if you are subscribing to this notion of macrorealism, there's no chance that the particle was disturbed because the light field was only acting on the right half of the well. Okay? So this manifestly implements this non-invasive measurement. Okay? So we are not applying quantum mechanics yet. We are saying that if the particle already had a definite state on one half of it and you were shining light on the other half, it should be disturbed. Okay, so in that sense, we are implementing what is called a negative result measurement. Tony has also argued that this is the nature of the measurement which is needed. What happens is if you really are doing negative result measurement, you are not perturbing the system by the action of the measurement, like just by the kick of the light. Through quantum mechanics, you of course can. Okay? And then this type of test become a test really of realism in that sense, okay, of macrorealism. Okay? And through this you can build statistics because half the time you can put the light on the other side and you can go on building statistics. Yeah. Okay. So you can build up statistics. Okay. And by building up statistics, what we do is we measure in various times. Okay, this is the famous Leggett-Garg inequality. You measure at one time, second time, equally spaced times, Ti and Tj we measure. Okay, now if you assume if these macrorealism postulates, then what happens? You see this QT2 is common between these, QT4 is common among these, and this is very easy. It's just like exactly the same maths as a Bell inequality. It's very easy to prove that if an object is, obeying macrorealism, this can never be larger than 2. Okay? And this we show you can violate. Okay? So what we take is we simply take a coherent state going rightwards with the momentum p, and we do these modular measurements. Okay? So if it's found on the left of the well, we give a value +1. If it's found on the right of the well, it's projected on the right of the well, then we give a value -1, yeah, ±1. Okay? And this way we build up the statistics. Okay? So it's a dichotomic measurement, but on a continuous variable system. And you can find the probabilities, and then of course you can propagate the system again for some time and again do the same measurement. Okay? And essentially we propagate the system for quarter of an oscillation, 3/4 of an oscillation. This is the time when position translates to momentum maximally, quarter of an oscillation. 3/4 is probably an artifact of the specific form of the inequality that we have used. Okay, so we need 3/4 of an oscillation time difference between these two time measurements. So what we are doing is we measure at one time, we let the system evolve for 3/4 of a period, again measure it. Okay, and with these two times we are building up these correlations. Okay, and when these were computed and for various masses and for various essentially for various masses, then we can find that there's always an optimal momentum you can find so that you get violation. Okay? And this violation doesn't stop. Whatever the mass, the violation doesn't stop. You can go for larger and larger masses. It just becomes very difficult. Okay? So you see A classical is the classical amplitude of oscillation. So you have to control the classical amplitude of oscillation finer and finer manner as you go to larger masses. Okay? We have taken these to be in traps of megahertz frequency, and typically people have already trapped things, actually quite large things, even these kinds of things. But we will hope for an experiment in this kind of domain to start with. So just what is happening, because I don't have a picture in the slide, essentially you can think of the thing just for a qualitative understanding in phase space. We are starting with a coherent state. You can picture kind of here. Yeah, this is x, this is p. Okay, so with the momentum. Okay, and when we are doing a measurement on the left or right, what is happening is we are projecting it to a, on one side. Okay, but this doesn't have just that effect. It has this. It injects a lot of momentum as well. You see, depending on left and right. Okay, and that is why this momentum cannot be too far from the center, because we want the disturbance. So what happens after this kind of time? We are measuring again. If it was a perfect classical particle, it would always be on the right of the well after that time. But since if we project and disturb the momentum, when we come here, we will get some negative momenta as well. Okay, so that is kind of the physical origin of this. This is the disturbance which leads to the quantum disturbance due to the projection to 1/2, which leads to the violation, and that can let us understand some of the features. For example, we need of course we need a non-zero momentum, because otherwise it's an eigenstate, it doesn't evolve. So there's a translation symmetry, so the violation goes away. But also things such that if you cannot there's a kind of optimal momentum, because what happens here is you require the spread, so this momentum cannot be very large. Okay, yet if its momentum is near the center, then there's not too much of a difference. So somehow some momenta here works. Okay, and if it gets too much thermal, then of course it also the violation stops. But we can tolerate about 10 to the power 4 phonons. Okay, so it also works. It's interesting that it works for thermal states. Okay, so this way you can prove ideally that a 10 to the power 6 AMU object trapped is actually quantum. Okay, And this is probably one of the earliest experiments they can do. Okay. Now, I go to over to this other aspect of Tony's, that Tony has raised. I mean, of course, these are both related, as I understand. Is Tony also launched this program that we should try to extend the boundary of the quantum world, which we are doing through the violation of macrorealism in the previous experiment, but more, another thing would be to just see whether the superposition principle is holding, okay, for larger and larger objects, okay. And what Tony proposed in this, classic paper of 1980 is that you take superposition of, billions of electrons going one way or the other, which is two different fluxes. Today we call it the flux qubit, where it has been demonstrated. So in other words, we test the superposition of, whether a superposition exists between two, large number of electrons flowing one way or other. Okay. And another technical point he emphasized is what are the kinds of superpositions which we typically do not see, which we are unfamiliar with. In this case, for example, all electrons are moving left or all electrons are moving right. Okay? Which is very different from something which occurs in a, say, in a BEC or in a superconductor, where you have each particle in a superposition and there are n of those particles. Okay? So what he told is that we should all try to generate better and better versions of this and check whether quantum principles are still holding true. If it is not holding true, that will be one solution to the Schrodinger's cat. But if it's holding true, that is still a win, because then these are even more exotic states and will have exotic uses in sensing and, and of course, that quantum mechanics holds up to a better scale. Okay. Okay. For that, again, we use these kind of nano-objects. Okay, but now we think of a spin inside. Okay, so there's an embedded spin. Okay. And what happens is that you create the embedded spin initially in a superposition of states, +1 plus -1. Okay, this results in the object, oscillating in two different wells. For +1, it is one well. For -1, it's another well. Okay, so you naturally can have an interference experiment. So at time t equal to 0, you prepare a superposition of +1 and -1. Okay, two wells. It starts oscillating, and then after one time period comes back. Okay. This is a Ramsey interferometry because there's this spin here. Okay, you do not ever need to measure the nano object itself. Okay, all you do is you measure the spin. Okay, so you need to give, of course, a relative phase between these two, which you can do easily by tilting it, for example, slightly. So the Earth's gravitational acceleration will give a mg height difference phase. Okay, and then you can purely, after one time period, still the objects will come back, and you can then purely measure the spin state, okay, and from by doing a Ramsey pulse from the probability of, say, getting a 0, okay, you can find out this phase, this relative phase. Okay. So this is how you can you can just do not need to measure, any particular object or anything, but you can only measure spins. Okay, this is purely Ramsey preparation and optical fluorescence, and you can measure. Okay. However, this previous scheme is working on one aspect of the macroscopicity. So this is the whole crystal is here or there, but there's not too much separation. Okay. So so one would also like to improve the separation, and for that, what we said is that you just drop from this trap and do a normal Stern-Gerlach effect. Okay. However, you do not do complete Stern-Gerlach. You do what is called Stern-Gerlach interferometry. So you flip spins after a time tau by 4, so that they start decelerating, turning, and then accelerating. Then you flip again, so that they come back to the same motional state. So this is an interferometry by flipping, where you really bring back corresponding to both the spin up and the down to the same motional state as far as both position and momentum are concerned. So when the motional states completely overlap, the spin is again unentangled from the system, and you can actually measure again the phase, relative phase, and thereby you can infer the interference. Okay. And you can also tilt to give a relative phase if you want. Okay. What is very interesting is that now with this scheme we can kind of go to microscale masses, so micrometer spheres. Okay, micrometer spheres have 10 to the power minus 14 kg mass, so that's the huge in terms of atomic units, and you can create and verify their superpositions. But what is interesting is that these are also Newtonian Schrodinger cats, in some sense that when a 10 to the power minus 14 kg mass is here or there, there's a significant gravitational field centered here or centered there. So we can also then try to test whether the gravitational field is satisfying the superposition principle. Okay? So far people were trying to see whether masses being here plus there is coherent, but you can also try to test now whether gravitational field being centered here or centered there remains coherent. Okay? But how would you do that? The big problem is if you do an interference experiment, then again they come back. Okay? It is not easy to test that coherence, okay, with the associated. It's always tied to the mass. It's centered around the mass. So this is why we propose this scheme where you actually prepare two superpositions, okay, next to each other. Okay, you have a superposition delta x and centers separated by a d, and you let them interact purely gravitationally. Okay, so you have to keep these two kind of interferometers, which put left-right isolation, separated by a distance of 100 microns. Okay, if you do that, then for this 100 microns, there's no surface forces. Okay, so there's no Casimir and other things acting. So they are separated enough. Then what happens is purely the Newtonian interaction will give phase evolutions. Okay, and so this is exactly like a control Z gate in quantum computation. Okay, left and right are like two Ising states of two Ising spins, and this is like an Ising interaction. Okay, and you can really entangle them. This is a control Z gate. Okay, and for a certain time evolution, when these phases, the difference in phase between that and that, it's really pi, then you end up with a maximally entangled state. Okay. The main observation that we had is that the advantage of that we can create now these superpositions of 10 to the power minus 14 kg microspheres. We can create these. Okay, so I'm a theorist. So when we can create, I talk with experimentalists, and they think they can create it. Okay, so these are feasible schemes. Okay, and about microns separated, if you can hold such a superposition for 1 second, then this is the numerical magic. Purely through Newtonian gravitational interaction, you can get a phase of nearly 1. Okay, because both these masses are kind of large. They're 10 to the power minus 14 kg. They're micrometer diameter spheres. Yeah? Yeah. So when you have micrometer diameter spheres, then it's possible to do entanglement in 1 second purely through the gravitational interaction. Okay? And it doesn't matter that capital G is so small, because of course here h cross is in the denominator. Okay? This is the energy by h cross, the frequency. So it amplifies that effect. So gravitational interaction can lead to an entanglement. Of course, you have to keep them separated enough, neutral enough for other interactions to not act, and this is possible for 100 microns. Okay. Now, the clever thing about using these kind of Ramsey schemes to create the interference is that spins are correlated with the spatial position. So when you undo this, what happens is the spins get entangled. Okay. So now the masses have both been brought back in the respective interferometers, okay, but the entanglement is purely, mapped to the spin. Okay. So you can measure what is called an entanglement witness, okay, which essentially amounts to measuring the spins in, more than one basis, the correlation. Okay. Then what happens is these two interferometers. Okay, so this part is we map to nuclear spins to let them freely fall beside each other so that the interaction gets time to act. Okay. At the end of the time, you just measure some spin correlations, and you can verify that gravity did mediate entanglement. Okay. Now, if the Newtonian interaction mediated entanglement, what can we conclude about the gravitational field itself, or the curvature, or the mediator? Okay, that's the question. Okay, we can conclude that it is quantum. Okay, it's a bona fide quantum entity. Why? Because you see these two interferometers, you can regard them as two qubits, okay, left and right, okay. They cannot get entangled if they and there's a mediator going between them, which is the gravitational field, okay. If that was classical, then we would have classical communication, and by local operations and classical communication, you cannot entangle two objects. Okay. So if this experiment, which is kind of not too distant, is done, then that will prove that gravitational field can be in a superposition of macroscopically distinct states, because without a quantum entity passing between them, you cannot create entanglement. Okay. And it is also easy to understand that physically why, right? Because to create entanglement, you need correlation more than one basis to flow from one place to another. So you need superpositions to go. Okay. So it's an indirect test. Okay. And what I say is that some people would say that, especially those who do canonical quantization, would say that you can consider the Newtonian interaction as an action at a distance. It's just a gauge constraint. That's one way of thinking of it. But you can also think of it as the exchange of a virtual graviton. Okay, that's equal. Yeah. So that is a quantum change. So how do you distinguish that and the classical thing? So this experiment will give a way to say that. And essentially, you can see also superpositions between gravitational field states are necessary to, show this generation of this entanglement. Okay. So anyway, so just to summarize, so this is the last slide. Okay. So we are stretching the questions asked by Tony in the 1980s. We are stretching them. So we are stretching the violation of macrorealism to up to nano-objects, and we are trying to stretch the quantum superposition principle to objects which have sufficiently distinct gravitational fields, and indeed trying to test whether even the macroscopically distinct gravitational fields can be in superposition. Thank you.
Thank you very much. Questions?
Yeah.
This is something we discussed a little before, but
okay.
I would just like to emphasize that it's important to, when one says that one can prove that such and such happens, it is important to specify what implicit assumptions one makes.
Right.
I think, of course,
it's a very good question.
To establish entanglement between macroscopic.
Yeah.
But I think one really should add the qualification, assuming that the quantum formulas is working.
Right.
If it isn't, then you really can't use anything.
No. Yeah. So I should clarify on that also. Yeah. So we did not, when we wrote the paper, we didn't write very clearly exact assumptions that we use. We wrote two assumptions. So one is that we need a mediator, okay, and we use this LOCC, local. Yeah. But what I've realized, essentially what we use, so if you see that picture there, so we are using essentially the fact that the locality of physical interactions. That is very important here. That's an assumption here. So if there was a direct non-local interaction, if this was eliminated altogether, I mean, people of course eliminated to get the Newtonian interaction, but we are assuming that it is a mass affects the curvature only locally, or gives off virtual gravitons only through a local process, and the other mass catches it, or the other mass is affected by the curvature created, locally here. So if it was just, fully in a non-local theory, we cannot use this. Yeah, that's the thing. So you have to have locality of physical interactions is an assumption here.
Yeah, taking this question a bit further, I've actually already asked you in some other meetings that just by saying that the gravitational field mediates entanglement It's hard to say that it's quantized because we have indeed experimentally proven entanglement of classical electromagnetic fields, which have been shown to violate Bell's inequality. So I don't know how far, so that's why, I mean, there is some other assumption going into this aspect that one is perhaps assuming a quantum nature of the, I mean, coherence of the individual gravitating objects. Because one has seen entanglement even at the classical electromagnetic field level.
Okay, yeah.
Says, we had heard from Singapore group, they had written a theoretical paper in optomechanical cavities, how to have entanglement between two mirrors, actually by optomechanical coupling. There too, they claim that it is quantum mechanical, but it is little tricky. We had argued about it there too. That is the gravity. Is it actually a quantum entanglement induced by gravity? That question remains.
So, I mean, in actual tests, of course, you have to be very careful of no other interaction acting, okay? So we have to, if you keep 100 microns, then for microspheres, there's no Casimir effect, okay? And of course, you have to keep neutral, you have to, physically spin these so that there are no multiples inside. So you have to ensure all those things, you are still far from any short-range unknown forces also. We are well outside that. You have to think it's oscillation, but I will think according to Tony's important point, whether there are any other assumptions also going in. I would think that the locality is the only assumption here, but maybe we need to, whether we are putting further structure implicitly, we have to think,
Other questions? Okay, if not, let me take a bit forward your first part of your
exactly.
So using it's a very nice setup. So using that setup, can you actually, because at one point perhaps you mentioned about coarse graining. So see, the point is that you assume a clear difference between the left and right halves. But in any actual practical situation, this will be fuzzy. So if you take coarse graining into account, you can see the emergence of classicality. If along with that, if you go to the limit of large masses. And in that context, it might be interesting to also try to test the NSIT condition. Apart from in addition to the LG inequality.
I mean, the big advantage of this thing, this work with Dipankar Da and Dipankar Home and his student, is the main thing is that this is the simplest. This is one of the simplest things like a next step on the pipeline. They have already trapped these things, but you're right. Something which we realized after the paper was published, so we do not have too much. We write it together with further calculation. Is that this measurement needs to be sharper than the individual coherent state spread, and this to be done within the time that the momentum the state takes to cross the middle. Okay, so it's a short window of time. So if you have large window of time, you can make any measurement arbitrarily precise. You go on shining photons 1/√n. Okay, but here you have to do it fast enough before it traverses the middle. So there are practical limitations there, and we really did not yet do the work with more realistic measurements. That's we are doing those. Maybe Dipankar can comment on that. We are trying to do those things. I think
since we are running out of time, if there are no more comments, then let us thank Sougato and both the speakers in the session.